equal, because we don't want to have to deal with acceleration, right? We don't want to have to deal with dynamics right now. So we're going to assume, or I'm going to tell you that F equals F, which is why I only wrote it once. And so my stress is force over area. And so you see here, we're compressing this rod. We're pushing it like this, right? So you guys ever do that isometric exercise when you're trying to push but you don't move? Is that what it is? No? Anybody? There's a thing where you get like tense up your muscles. No? All right, so we're pushing, right? And the area that we care about, that is the cross-sectional area, right? So if our force is applied to a plane, it's the area of that plane. If I was pushing instead in this direction with my force, we call that F2 and F2. So if I was pushing in that direction, what would my area be? Would it still be pi r squared? No. No, I would have to know something about the length, right? Because my area would be that cross-sectional area against the direction that I'm pushing. So is that clear? Our stress, so stress happens when stuff pushes on us, right? Stress happens when your homework's due. Stress happens when, I don't know, what else is stressful? Big tests. Having to apply for an internship. So stress happens when stuff pushes on us. And so our life stress is the same as engineering stress, except you can put different units on tests than you can on forces. All right, so stress is happening when stuff pushes on us. Strain. Tension. No. Just kind of wear us down. I'm not sure if it's the stress or the strain that wears us down. So what's strain? So strain happens when our part changes shape. When something yields to stress. Oh, then there's this thing called yield stress, right? Which isn't what you meant. Now, let me get the slides up. So we've got our stress. So strain is the result of stress. Strain is what happens when we apply a stress to something. And so when we're talking about our rod there, when we were compressing our rod, before we applied any force, it had a length, right? We'll say that before we applied stress to it, it had a length. After we applied the stress to it, what happened to the length? It became smaller than the original length if this is the direction of our force, right? So when does it get smaller? How much does the force have to be to make it get smaller? Are there any times that it doesn't get smaller? When? Are there any times that it doesn't get smaller? It will always get smaller. The only times it doesn't get smaller is when we can't measure the change. But it is getting smaller. If we had a better measurement tool, we would find that it gets smaller. So every time we apply a force to something, we change it. And so strain is simply the initial, so the new length minus the initial length divided by the initial length. And so that's our definition for strain. So we have stress is force over area. Strain is what happens when we apply a stress to something, and it's simply the change in dimension. Is that good? So what, do all things change dimension the same way for the same stress? No. How do we know?
Because not all materials have the same consistency.
Not all materials have the same consistency. Anybody remember physics class back in high school? What did we call this? This was a law. There was a law that defined how much stuff was going to change shape when you apply a force to it. Anybody remember? No. There's a great YouTube video. It's about 16 minutes long that explains this topic way better than I ever could. So what I'm going to do is I'm going to start that video, and then I'm going to give you a couple talk. You guys laugh. I did that once in class. I came up, I started a video of me talking about the topic of the lecture, and I walked out the door. I came around, it was this room, I came around to the back door, and I snuck back in, and we looked at each other, wondering what they were supposed to do, if they were supposed to stay and watch the thing. It was a lot of fun for me. I don't know if it was fun for them, but it was a lot of fun for me. Seriously though, I'll send you the link to this YouTube video. It's an excellent YouTube video that talks about this. But what he talks about is he talks about Hooke's law. And so Hooke's law tells us about the, what do we get from Hooke's law? Anybody? So yeah, Hooke's law deals with this spring force thing, right? And so he talks about Hooke's law, and he talks about this thing called elastic modulus. And so who's had stress and strain here? Nobody shouted out elastic modulus. When I said what makes them different. Nobody? So how do you determine elastic modulus when it's had stress and strain? So what's the elastic modulus of a piece of a material? When did you take the class? Who took the class this year? Stand up if you took the class this year. You guys already raised your hand, now you're going to stand up. All right. Oh, it was sort of a pausing stand there. I forget your name. Eric. So how do I find out the elastic modulus of a piece of material? Say I have this piece of chalk, and I would like to determine the elastic modulus of the piece of chalk. What's the experiment I would do to determine that? It doesn't have to be this piece of chalk, it could be a rubber band. What do you got? Alright, so I could measure its length, right? I could apply a known force to it and see how much it changes the dimension. Does that tell me the elastic modulus? What else do I have to do? I had several conversations with you. I should remember your name, but I don't. Travis. I just remember you're the guy from Norwich. That's it. See. What else do I have to do besides apply a force and measure the change in length?
I know that it's stressful.
So what's stress over strain mean? If I want to do an experiment to determine this, what do I have to do?
We always did it one break.
Yeah, it's fun when stuff breaks, but what do I got to do? You get your hand up. You know the answer.
We need a load. We need the area for that area.
So we need the cross-sectional area, sure. So I need to calculate the stress. So I need to know the force and the area. I need to measure the change in length. Do I have enough information? How do I do it? So what I have to do is I have to take my stress. That's a symbol for stress, right? Yeah. I have to take my strain. I actually made a little note card so I wouldn't forget the symbols. I was looking up when I needed them. Make my stress and my strain. And I do an experiment. And I'll do this stress, and I'll measure the strain, and I'll plot the point. I'll do this one, and I'll plot the point. And I'll do this one, I'll plot the point. I'll plot the point, I'll plot the point. And I'll get something like this, right? Now, my points don't line up on that line. Why? Yes.
Because in real life,
Yeah, we can just end the sentence right there, because real life, period. Right? So there's experimental issues, there's measurement uncertainties, there's things going on. We do our experiment. We do a line fit to this. We do least squares regression of that. And so what's our strength, our elastic modulus now? Somebody said it earlier. It's the slope of this line, right? So we get stress to rise over run. Right? So E equals rise over run. So we can determine the elastic modulus for our material by doing an experiment. How else could we determine the elastic modulus for our material? Yeah. I have not tried this one using their universities. Okay, Google, what's the elastic modulus for aluminum? It's just the link to the page. I like it so much better when she reads it to me. But look at that. Wait, look at that. So Young's modulus, we call this. Big E. This gives us, I don't know, it's in there somewhere. I need to click on the link. So we can go to a reference manual if we want to find out what the elastic modulus for our material is. We're manufacturing engineers, who cares? Why would we need to know the elastic modulus for a material? Just as engineers, who cares if we're manufacturing engineers or not? Why would we need to know?
otherwise, we might just calculate how far a cut will go.
So it will actually impact, the cutting and the cutting forces and the cutting operation. Yeah. So if we're the designer, then we need to know, is this thing, so who said yield stress? Somebody said the word yield stress earlier. No? Oh, okay, I said the word yield stress. Sorry, that was me. I said the word yield stress. So when we do our experiment here, would you believe that it's not a perfectly straight line? And so what happens? So somebody that's had the class, it goes like this, right? At some point, what happens here?
That's where plastic deformation is.
That's where plastic deformation happens. So when we're in this region of the graph here, when we're in this stress strain region here, if we push on it and we let go, what happens? It goes back to what it was. When we get up here and go up here, if we push on it and let go, what happens? It stays pushed on. It comes back a little bit, but not all the way, right? So this is when we have yielded the material. We've gone into our plastic regime. And then, what's the next thing that happens after that? Right? Yeah, chalk does not get a big elastic region, does it? That's it'll break. So as the designer, we need to make sure our stuff's not going to break in the loads that we expect it to see. We need to make sure that it's not going to plastically deform under the loads that we expect it to see unless that's part of its function. When might we want to design something to plastically deform? Crumple zones on cars, yep. Modeling clay, yeah, and then you do a heat treatment process to make it stop being as, what's the word there? Malleable, right? And there is Play-Doh.
Oh, and foil.
Yeah, right. It'd be interesting to study the mechanics of crumpling up tinfoil to cover your food. I haven't thought that through, but there's certainly elastic and plastic deformation going on. Yeah, I think tinfoil counts. Aluminum foil, whatever we want to make it out of. All right. Where was I? We have elastic modulus. We might care about the elastic modulus because we want to make sure our parts work. As the manufacturing engineer, why might we care about elastic modulus?
If we can make the part without overmake or creating the part, so it's the minimum of
Okay, I think deciding like how much material the part needs to have falls on the designer, and that gets back to that first question. Will it withstand the forces it needs to see in use? So, as the manufacturing engineer, why might we care about elastic modulus, stress and strain? Go ahead, Alexa. Say again? There are. So in that, remember we had our drawing there, where we have the tool here, we've got the workpiece going here, the chip is going that way, and new surfaces over there, right? So what's happening here? At the place where I do this dashed line, what's happening there? That's where the chip is forming, right? Everything over here is workpiece material. If only I had another color, look at that. Everything over here is chip. And so right here at the boundary between workpiece material and workpiece material and chip, there's a thing going on there called dynamic shear stress. And so we're going to actually, at the end of today, go through calculating that dynamic shear stress. So we absolutely care about that. But it's simpler than that. You don't even have to care about the mechanics of chip formation. So as engineers, we're supposed to care about geeky stuff like the mechanics of chip formation. But if you're just a machinist, if you're a master machinist or a tool and die maker, but you don't care about the mechanics of chip formation because you decided not to, then you still care about elastic modulus. You still care about stress and strain. Why is it? Xavier. Yeah, no, that's the tool designer's problem. We just won't buy them if they break, right? We'll buy them once, but we're not going to buy them again if they keep breaking. Why do I care? What do I have to do to cut my part? So.
We don't want them to break.
Yeah, we don't want to break it, but that's. If you screw this up, I agree, the tool will break. But it happens before the thing that we care about happens before the tool breaks. So what happens how do we hold our workpiece in the machine tool? Many times we hold it in a vise, right? How does a vise work? You could hold it by hand. I'm trying to think of an example where I've seen that. Not usually in production.
Both ends of the vise.
Yeah, so when we want to fixture something in our vise, let's see here, we have the workpiece. We'll call it WP. I don't recommend kind of ceremonies that happen for the classes to show up on the tour. I have a workpiece. It's got a rough edge. We have a vise jaw. I always want to write the wrong kind of ice there. We have another ice jaw. I'm going to make little model pieces for the next time. So, all right, so I put my workpiece between the vice jaws. Now what do? I turn the handle, right? As I turn the handle, I apply a mechanical advantage by turning a screw. That screw moves these vice jaws closer to each other, right? What keeps the workpiece in the machine tool during the cutting operation? What are the forces acting on the workpiece during the cutting operation? We drew a three-body diagram of the workpiece. So I got my workpiece. What else do I need? So I got a load on this side. Right, so I've got a distributed load. And instead of drawing it like that distributed load, we could just try to F and F. Right? All right, so I got my workpiece, I got my forces. Now what else is on there? What are the other loads on the workpiece? Gravity is going this direction, right? Point it down. What do we draw that? Like this? Well, hey, what's this force? I mean, yeah, there's vice jaws pushing on, right? Yeah, all right, so I got, this one is the tools. I got this one here, that's my gravity, right? We can assume that those are evenly distributed. Once gave an invited paper. I was studying surface metrology. I was studying how the surface of a cornflake changed over time after exposure to melt. Kind of a fun thing. I totally did it just for fun because, well, I had some cornflakes, I had some melt, and I had the machine to measure the surface. So I actually did this time study where I did repeated measurements of that surface, and I was able to show that with like a 99.9% accuracy, if I had the measurement of a cornflake that exposed to melt, I can tell you how long it had been in the melt. That was a pretty cool result that came out of that. Have a little fun little experiment. The thing scratched too late at night. And I was invited to talk at a food conference, a conference about the measurement of food. This is a pretty cool thing. I get in there to give my. So what I wanted to do was demonstrate the data analysis method that I was using, because it could apply to lots of things. That was my goal. Talk about the data analysis method. In the room was the most renowned world expert on milk, and all of the people that hang out with the milk expert. All of the questions were about the milk. Nobody cared about the cornflakes. Nobody cared about the analysis technique. They wanted to know what kind of milk was it? What was the temperature of the milk? What was the fat content of the milk? And then, so we were joking about that because they got it, but I didn't care about any of that. We're joking about it. They said, yeah, well, when we look at this stuff, we just say, imagine a spherical cow with a homogeneous distribution of milk. Right. So we're going to imagine a cubicle, right? Cubicle, that's the word. A cubic item here with a homogeneous distribution of forces. Right. So we got force pushing down from gravity, force pushing up from the parallels, right? The thing that it was sitting on before we did that. We've got friction. We've got normal forces, and it's just sitting there, right? Nothing's happening. In comes the cutting tool. Wow! Jesus, sound when it comes into the material, right? In comes the cutting tool. What else have I got for force now? I've got friction and cutting force, right? And so what direction is the cutting force? Just think about the shape of the milling tool.
It's in many directions.
Well, no. You can, in a moment in time, it has a direction. What do you think? What would be a candidate direction for that cutting force? So there's going to be some component of it that's lined up with FC, right? FC is going to be lined up with the direction, so the instantaneous velocity from the direction of rotation, right? So at that moment, some component of it's going to be coming straight at you this way because of the FC. So if you look at the milling tools critically, what direction is the cutting edge? It's not like up and down, right? The cutting edge is a spiral that goes up that tool or a helix on the tool. So it's actually going to be sort of this direction, kind of up, kind of to the side, and then it's going to go like this as the tool spins. There's always going to be a component in which direction? Up. And half the time, there's going to be a component parallel to the vice jaws. Half the time, there's going to be a component perpendicular to the vice jaws. What keeps the workpiece from flying out of the machine tool? Friction. What's friction force equal? Right? F equals mu times m. What do we do when we want more friction? We have two things we can do, right? We can change mu, or we can change n. What happens when we change n? The stress changes. What happens when the stress changes? The strain changes. So if we have a material with a very high elastic modulus, does that make it more squishy or less squishy? A high elastic modulus is more squishy. I don't remember. I have to look at the graph to figure it out. Steel has higher elastic modulus than aluminum, right? The steel is less squishy than aluminum. We have a data point. Less squishy. So if I have a material with a high elastic modulus, and I add more normal force, what happens? Less than if we had a lower elastic modulus, right? Okay. Why do I care? You know what? That comes up in tomorrow's lecture. Right? Because the butter also had a low mu. Right? So, if we want to have a higher rolling force, we need to have a higher frictional force. Why would we need a higher rolling force? When we have a higher cutting force. So, what materials have high elastic moduli? What material? So, name some materials that have pretty high elastic moduluses. Steel, stainless steel, titanium, cast iron, right? What's some materials that we might want to machine that have low elastic modulus? Besides butter. Plastic, aluminum, brass, rubber. Gold is a pain in the ass to machine. Really hard to hold on to. Really squishy. Silver. I have not personally machined gold, but I have machined silver. So these things have. What's going to happen? What's going to happen if we? All right. How are we going to reduce the stress then? So we just want to reduce stress. So we can increase mu, so we need a slower m. N, sorry, we can do that. Just in general, how do you reduce stress? I got a theory.
What's the know?
I don't think yoga does it. It violates my theory. Right? If stress is force over area, I know how to change area. Eat more. Less yoga. Alright. So here's our example. We've got our part in the vise. That is like my favorite slide that I ever made. Picture that on my refrigerator to remind me to keep the door closed. So here's our part in the vise. We're applying our normal force. What has happened? Alex, you're scratching your ear. Looks like you're raising your hand. What do you got? What has happened when we applied our normal force to our workpiece? So the possible friction force available has increased. So we can use a higher cutting force if we've applied our normal force. What do we know always happens when we apply a normal force to our workpiece? It changes shape, right? Preferably not plastically, right? But I've seen it happen, especially with the butter. The butter definitely changes shape plastically as it thaws out and its modulus changes. All right. So can I calculate the stress based on what I see here? If you assume that this A stands for area, if you assume that A stands for area, then we can calculate the stress based on what we see here, right? Perfect. Then we've got our frictional force equals F times N times, or equals N times mu, right? Okay, that's going to keep us from pulling the workpiece out of the vise. So I can determine how much cutting force I can withstand, right? By knowing what N is and mu is. How do I define mu? How do I know mu? Right?
It depends on the material.
Okay, Google, what's the frictional coefficient between steel and aluminum? All right. Thank you.
Thank you.
Friction coefficient for aluminum and steel. Hey, again, the link to the Engineer's Toolbox. That's a good website. Google likes the Engineer's Toolbox. All right, but you can look that up. You can look that up. All right, so we can figure that out. If we know how much friction force we can have, can we then estimate the appropriate cutting parameters to machine our part? How are we going to do that? We can estimate how much power it takes to make a cut, right? And what's the power of this cut depend on, in broad terms? The material, the volumetric material removal rate, right? Q, and then some parameters that have to do with the machine tool, right? So the factor that we can impact with our cutting parameters, other than changing machine tools, is that Q, right? So the material removal rate, we can impact that. What goes into material removal rate in a milling machine? Incremental depth, width of cut, and speed, right? That's what goes into the volumetric removal rate. So if I'd like to have a lower, and the cutting force is directly proportional to the power, right? If I'd like to have a lower cutting force, what should I do? I could go slower. Turns out the tooling manufacturers don't like us to go slower. Tooling manufacturers want us to go the speed they told us to go. What can I do? If I'm not going to change speed, what can I do? I can change incremental depth and step over, right? Typically, the one that we attack first is incremental depth. We take a smaller cut. We make a smaller chip. Your cut time goes up, your cutting force goes down. Okay, that's good. So we can calculate based on knowing the material properties and the machine tool that we've got. We can figure out, is it possible to make this cut? What's our other limiting factor? What else are we going to care about? We're going to care about how much the part is deformed, right? Right? Because we like to have the part not deform so much that we notice it in the finished part. Because what happens when we machine our part, when we machine a pocket in the part of that shape? What happens when we let go of the vise, when we unclamp the vise?
The pocket and the wire.
Pocket changes size, right? And so if we've got a tolerance on how closely we have to hit this pocket diameter, then we can determine the maximum allowable clamping force. And based on the maximum allowable clamping force, we can figure out the maximum power that we can use. So what are we going to do when we're figuring this out? Because we said the cutting force is this direction, right? So he's going to say right and stop. Right. Cutting force is in this direction. What are we going to do when we do our estimate? We don't know how much of it, we don't know what the angle is. Just from the math that we've just explained doing, we can't know what this angle is. You can figure it out with more complicated math and with finite element analysis. But we don't need to. We want to do this on a napkin, right? Back of an envelope. So what should we do when we do our calculation? Assume that 100% of the force is up. It's never going to be more than 100%, right? So we can assume that 100% of the force is up and that gravity equals 0. Right? Then our part's not going to fly out of the fixture. If we want to know how much the pocket's going to change size, then we can do this little, it's like, what's the thing where you do the two fractions? There's a thing in math, right? Well, there's the thing where like x1 is like x2, x1 over 2. Right, there's this thing where you do the equations, and you find the missing one. Yeah, you could do stuff like that. You could just copy the equation off the slide. I don't care what you do. You can figure it out. You can all derive this, right? You all know enough to derive this. A good friend of mine and I have this ongoing debate about whether we should tell you equations or maybe derive equations. And I'm pretty sure that if you know F equals MA and some other basic principles, you can derive all the equations you need. But this means I can memorize things. Bring these so that I can know what's coming next. Dynamic shear stress. We'll start with dynamic shear stress tomorrow. I'm not sure tomorrow was listed on the original syllabus. Well, I think I want to have class tomorrow, but I'm not sure if it was listed on the syllabus, so let's check. So somebody asked at the beginning of the term, I'm not sure if everybody heard the answer, but there's this question of that first Thursday when we didn't have any class, and somebody asked me if I canceled class that day. I said, no, I didn't cancel it because it was never scheduled. And so the way that the class typically has worked, and this has been going on for years, there's like 21 time slots scheduled for lecture. We only use about 14 to 16 of them. And so having the 3 days a week allows some flexibility in case the faculty member has to travel or something like that. So I don't think I originally scheduled tomorrow. What day is it now? Today's the 9th. I did not originally schedule tomorrow, but I can fix that. And that is C16, right? Look at that. Group projects are due tomorrow, right? What time? Midnight. And any. There we go. Dynamic shear stress and any group projects questions you have. Stuff you can't figure out how to solve the problem. Things like that, yes.
Will you be checking the special voice questions?
I should be, and the PH should be also. All right. Hey, we finished a minute early. We're going to back now.